Okay, so today's question is 311, sparse matrix multiplication. We are given two sparse matrices, A and B. We need to return the result of AB. So because it's this order, AB, we need to have that A's column number is equal to B serial number. So the example here we have matrix A with 3 rows, 2 rows, 3 columns, and matrix B, 3 rows, 3 columns. As a result, their matrix multiplication result, if we call this matrix C, then it needs to have the same number of rows as A and the same number of columns as B. So it's 2 by 3. So for this for every particular cell values in here, let's say ij, the value of ij, Cij, is the dot product between the ith row from the matrix A and j's column from matrix B. So this particular number, say 3 here, because it's the second row and and third column, that's 2, 3. So it's the dot product between the second row from A and the third column from B. So that's the sum of 0 multiplied by -1, 0 multiplied by 0, and 1 multiplied by 3. So that's the result, number 3 here, you're saying. So just think about this in terms of time and space complexity. Just for the sake of easing the math, let's say that we have square matrices. So instead of this 2 by 3, let's think of that A to be m by n, B to be m by n as well. As a result, the output matrix C is going to be m by n. So for the number of elements in the final output is going to be n squared elements. For each of those elements, we need to do the aforementioned dot product to get that value. That dot product, it's by itself an order of n calculation. So in total, the time complexity for matrix multiplication in this most straightforward way is going to be cubic time, n to the power of 3. And for space, the output matrix, if we store that in this dense format, it's a n squared space. But that's for the output, and we don't need any extra space to help these operations. So that's the most straightforward way of if we are implementing this as a dense matrix. But actually the question here, it gives us a dense matrix. You see here we have A to be list of integers. So this is a dense format. We're going to have a lot of zeros actually stored in this input A and B. So I think the purpose is not really of this question is not really to outputting this C, because it's expecting the C to be in dense format as well. If you just code the standard matrix multiplication using their dense format, I think it would just do fine for this for the online judgment systems perspective. But I guess I think the question is asking us to at least code up some kind of design, at least the design class for sparse matrix, and also have the class method, have the method for multiplication. So the question gives us a link to this, but I guess for the interview purpose, the interviewer is not going to give you all this information. And just looking at the contents, you can see there are quite a few options of how to implement a sparse matrix, and there are pros and cons of all of this. Without reading that, you can pretty much guess that some may be easy to create, some might be easy to store things, efficient on the memory side, some may be a little bit time consuming to construct or take more space, but they might be facilitating faster computation. Standard trade-offs here. So I guess that if you're from scientific computing kind of background, you might know the detail of this CO, CSR, those type of format. But I guess for general coding interview purposes, the dictionary of keys might be the ones that comes most natural for you to code it up. And the idea of this representation is also really simple. It's just the hash maps with the location in the matrix as the key and the cell value as the value. So it's the tuple of row and column mapping to the actual value in the sparse matrix. If the cell value is 0, you just don't have that entry in the dictionary. So that's going to be the implementation I will be doing here today. So yeah, the rest is just coding this thing up. It's actually quite boring, this question. So let's say we have a class called sparse matrix. So let's see that we're coding up a class method to create a new object of this particular sparse matrix class. Let's call it frontends, which takes in the class itself and a matrix. What we will grab is the number of rows and number of columns. If we say the dense matrix is the same as the one that the question is given to us, list of integers, then the number of rows is the length of n, and the number of columns is the length of the first row of that matrix. And we will convert this matrix into a sparse matrix. We will implement this method fairly quickly. To sparse, and we just construct a new object of this class. And S. So in order for this to work, we'll do a constructor here. Columns and the sparse matrix S. We're just setting values. S equal to S, just for consistency. So then we need to code this method. This will be a static method. To sparse, which takes in a dense matrix M, and we using a dictionary of key implementation of sparse matrix, and just for row. The row number and the actual list, row list, and the dense matrix for the column number and the cell value in looking at the individual cell values in that row. If the value is not 0, what we'll do is to create an entry in the dictionary. And After that, we basically converted the dense matrix from listed to integers to the location to value dictionary. So we'll just return this dictionary as the result. Let me rearrange the order of these two methods. So now we coded up the sparse matrix representation of DOK, dictionary of keys, representation of a sparse matrix, and the method to convert dense matrix into sparse ones. And then we need to implement the matrix multiplication. So we'll take another matrix B, maybe other. Let's just call it B then. So let's say we're saying that C is the output matrix, which will be a sparse matrix as well. A is just the self S, and that's so then the reason I'm grabbing another reference is just to trying to make it more like A multiplied by B equal to C. So for we're looking at so there are multiple ways we can go about implementing this here, but essentially it's doing the dot product. It's the rows dot product with the columns to as a result of the individual cells there. But here we are looking at sparse representation, so we're not actually gonna grabbing the whole rows, but instead we're gonna do element thing. So for this particular number, let's say that we're dealing with the 3 here, because it's the second row and third column here. The result, the values in the output matrix they're gonna have to involve some kind of calculation with this particular number 3 here. Is gonna be because it's gonna be this row would do dot product with this column to get to here and here and here. So the possible values in the output matrix that's possibly going to be affected by this particular cell here for A is going to be the rows here. So it's going to be the same row as the element that you are looking at from the A matrix. So for row and column and value, A var in A items. The only thing that's going to be affected by this particular A value is going to be it's going to be C row and something. That's the only possible cells in the C output that's going to be affected by this particular cell. For that, we need to scan the the correspondent values here. We're still sticking with this number 3 here. We are looking at each column, and we are looking at because this is the third column, we're actually looking at the third row, the third element of this column, these 3 different columns. If we have a number at the third position, then we would do the element multiplication and add that particular number to the to this location. That's 0 multiplied by 3. That's how much this is contributing to this cell value here. And frankly, the only thing that's going to be affected by this 3 is this 1 here, 1 multiplied by 3, and we putting that number here. So we're gonna scan through all the columns from B and try to see if there are any row that if there are any column that we have the i's element that's non-zero, where the I is equal to the columns of the of this value here. So let's see that we got the columns of B. We'll do a little bit just to keep track of things a little bit better, to annotating what rows and columns we're talking about in range B dot columns. If this AC, BC, the key exists, then we will grab the value of the of this element here is B, BC, BC. The output is gonna be here. So the same rows as 3 here, and it's the same column as this one here for this location. It's gonna be c.get zero and plus a val multiplied by b value. So we're gonna return a sparse matrix to say self to sparse from sparse. We'll code up a class method for this as well. So, what do we have? So self, the output C is going to have the same number of rows from the matrix A, and it's going to have the same number of columns from matrix B. And it's gonna the sparse matrix dictionary of key representation is generated here. So that's gonna be that. So this B is actually not the actual matrix, it's the object of this class. So what we have here is we should have b.s. Let me quickly fix this. Okay, that's more like it. So we'll code this thing up as well. From sparse CRS, non-column, and S. We're basically just calling a constructor. So yeah, this will do. So that's the sparse matrix class. We have a method to convert a dense matrix to sparse, we have a class method of creating object of the class, instance of the class, from either sparse or dense representation. We have a method of doing matrix multiplication between the instance of this class. We can do some checkings here. So let's see if we have anything. Oh, okay. The result is it's gonna be a dense one. So yeah, let's code another thing. Let's code a class method. Not a class method. Let's code up a method to convert this to dense matrix. Self. So we're gonna initializing the dense matrix to be all zeros for multiplied by self the number of columns, and we have a number of rows stored. So that's initializing a dense matrix for each of the values we know. Self s row and column is equal to that value, and we just return items. Otherwise we just enumerating over the keys. We have to do this. So that looks fine now. Then the remaining thing is just to do return that's converting both A and B to sparse matrix and do the multiplication and then converting the result back to sparse. Okay, so A is equal to sparse matrix dot from dense. We'll do the same thing to B, and C is just matrix A dot mat multiplication B, and we're returning the dense format of C. So yeah, I think it's pretty much this. Let's do some checkings to see if we have problems. The constructor is taking a sparse matrix, number of rows and number of columns, and just setting these instance variables. The toSparse method, we're taking a dense matrix. We initializing the sparse matrix to be an empty dictionary. We're looking at the rows and columns, the actual cells of this dense matrix. If the value is non-zero, we create an entry in the dictionary with the location mapping to the value, and then just return that matrix dictionary as the sparse representation of the sparse matrix. The from dense method is to just grabbing the number of rows and number of columns and calling this toSparse to convert the matrix, dense matrix, into a sparse one, just creating an object of the class. Here the from sparse is basically just calling the constructor. The matrix multiplication method, we're grabbing the, you know what, let's actually change this to self.s. initializing a empty dictionary, we looking at the cell values in the matrix itself, which is the A. Then we're trying to look at the element that we should do this element-wise multiplication between this particular value and whether we have a corresponding value to do this multiplication with that value here. If it indeed exists, we will update the entry in C. The rules seems okay, right? The rows, columns here is corresponding to here, right? The AR here is the AR here, and the AC here is the will become the rows that we're checking for the column-wise the vectors. We're just checking all the columns. If somehow just we have a number that needs to be multiplied by a val to update the cells here, then we grab that value and set this thing to from initializing to be 0 and just updating that with that. So it seems all good to me. This is okay. Yeah, this is okay. The dense matrix conversion is to initializing a list of the zeros. Those columns, that's the right order. And for the location and value mapping that we start in the sparse representation, we just setting that values in the dense format and return that. So from dense. Yeah, it looks right to me. So let's try to run it and submit. Okay, it was working. 80%. Okay. I'm curious. Let me actually do this. Can I use the? I might be able to overload this. Okay, yeah, it's this way, yeah. Cool. So this add operator in Python things 3.5 is the matrix multiplication operator, and to override this, you have to implement $matmul, which is what we have here. Okay, so I think for the sake of this problem, this works, but for the time and space complexity using this, it's not much faster. It's not faster than if you just do the dense version of this multiplication, right? Because we have the overhead of converting the dense format into the sparse one, which is let's analyze this a little bit. So the conversion happened here is calling this toSparse method. So this is squared. We have a squared operation to converting the do this to conversion. So n squared and this itself is let's just call it OK with k be the k may be the necessary operation we need to do this. Yeah, it's actually faster than if we just do this using a directly using the formula, taking the rows from A and multiply by the dot product with the columns from B. That's cubic time. But this, we use square term to convert that into a sparse matrix representation, and we'll be only doing the work we will need to do. Because you see we have a double loop here that goes through all the elements from A and checking the corresponding elements in B. So if this matrix are relatively sparse, this is going to be much faster than we do the full dot product ourselves. Yeah, so this is the solution. The K will be the what's that? This will be roughly, if the two matrices are randomly sparse, I think this K will be roughly proportional to the non-zero elements in C. That's my gut feeling. I'm not proving it here. I need to look it up later on, and I'll drop our comments in the section.